Welcome to the Delta podcast, where our goal is to bring together top engineers and researchers. Today, we are very, very, very lucky to have Pradeep Ravikumar. Welcome to the podcast.
Yeah, very wonderful to be here. Thanks for having me.
Of course, of course. So Pradeep, you've done a lot of really, really, really great stuff over the trajectory of your career. And so I guess we'll just start off by learning a little bit more about you and your background. So, you grew up in India. You went to what is one of my favorite schools for sure in India, which is IT Bombay. Maybe tell us a little bit more about your undergrad experience, sort of like what made you want to get a PhD.
Yeah, at IIT Bombay, actually, I started off doing. So this was the time when Google was just starting off,
Mm-hmm.
uh, and at that time, information retrieval was a very, very interesting topic, primarily because
Mm-hmm.
of Google showed that you could do very, very interesting things. You probably haven't heard of Alta Vista, which is a horrible search engine, and
Yeah.
Google just changed everything. And so that was actually what my bachelor's research project was on.
Mm-hmm.
And I thought that that's what I wanted to do research on. And in
Mm-hmm.
fact, um, when I started my PhD for the first couple of years,
Mm-hmm.
that's what I was focusing on. A lot of the work kind of dovetailed into machine learning, where
Mm-hmm.
um, we're looking at things such as some of the work that we did was turned out to be of relevance to the Census Bureau, and
Mm-hmm.
actually it's some of my higher sided work, incidentally, the first 2 years of my PhD
Mm-hmm.
on this information retrieval, where if you have let's say a record from some table and
Mm-hmm.
you want to figure out from some other table, is it the same record or not?
Mm-hmm.
And so this kind of stuff is very, very relevant in census bureaus where they have surveys in multiple waves. It's of great relevance in background checks. If
Mm-hmm.
you undergo background checks, they want to match you to a whole bunch of bad guy records
Mm-hmm.
and just check, is there a match? And yeah, there's a funny story of me being an expert witness for a case, but maybe that is for a
Yeah.
podcast. But yeah, I think so. For the first couple of years, that's what I was working on, and I took a machine learning class,
Mm-hmm.
and I thought this is what I want to do.
Mm-hmm.
And so after 2 years, I then shifted to machine learning.
Mm-hmm.
And yeah, ever since then, I've been in the field of machine learning. At that time, so this was actually, I see a lot of similarities in the trajectory of AI and machine learning.
Mm-hmm.
Um, if you look at stuff from the 80s onwards and look at stuff right now in AI from late 2010s to early 2020s onwards. In
Mm-hmm.
the early 80s, there was a huge amount of investment
Mm-hmm.
in expert systems, which are these rule-based systems.
Mm-hmm.
And people thought this is the end state of AI,
Mm-hmm.
where, at that time, companies were spending, hundreds of millions of dollars, and,
Mm-hmm.
inflation adjusted, it's probably the same as what
Mm-hmm.
is right now. And people thought, okay, this is the thing, and AI,
Mm-hmm.
as a whole, machine learning wasn't a thing at that time.
Mm-hmm.
But thought that this was the way to proceed. But then there was a small vanguard of, of some researchers
Mm-hmm.
who then created this subfield of machine learning, which
Mm-hmm.
now subsumes all of AI
Mm-hmm.
almost.
Yeah.
And that had a resurgence in the 90s and in the 2000s when I did my PhD.
Mm-hmm.
There was this big goal
Mm-hmm.
of having AI that is not only practical, not only something that works,
Mm-hmm.
but that's rigorous.
Mm-hmm.
And this was actually PTSD from the AI winter, where the people are just trying to do things that worked, and then eventually, that train stops.
Mm-hmm.
Because you need something that's reliable, you need something that you can guarantee works.
Mm-hmm.
And so that was really the big focus
Mm-hmm.
in the 2000s. And what I actually did my PhD
Mm-hmm.
in machine learning at Carnegie Mellon,
Mm-hmm.
and at that time there were a lot of um, researchers who said that you need to understand
Mm-hmm.
statistics, mathematical statistics to a very, very deep degree.
Mm-hmm.
And so after finishing my PhD, I did a postdoc in statistics in the statistics department at
Mm-hmm.
the University of California, Berkeley.
Mm-hmm.
But it was uh, between statistics and EECS,
Mm-hmm.
because that's what machine learning was really to a lot of the researchers there,
Mm-hmm.
including, leading researchers at
Mm-hmm.
that time and even now.
Mm-hmm.
And after that, I started my faculty position at University of Texas at Austin,
Mm-hmm.
in the computer science department there.
Yeah.
And because, again, I always had this um, um, notion, again, instilled in me by a lot of these leading researchers at
Mm-hmm.
CMU and Berkeley, that statistics is a crucial, mathematical statistics
Mm-hmm.
specifically, is a very crucial ingredient in ML,
Mm-hmm.
AI. I was part of actually a group that included an ex-provost to create a new statistics department at UT Austin. They didn't have a statistics department.
Mm-hmm.
And so we went to all of the steps that you need to take to
Yeah.
create a department. And so that was, I thought, something that has paid off greatly, because I think UT Austin right now is very strong in ML,
Yeah.
because they have all of the underpinnings.
Mm-hmm.
And then after that, I actually spent a year at a hedge fund,
Mm-hmm.
and then came to CMU.
Mm-hmm.
Um, and that's where I've been since.
Yeah, yeah, amazing. Okay, very cool. And I guess throughout this time, you were also involved with a lot of other, things. I believe, JMLR, for example, is one thing in like one initiative that you worked on. And also, I think you also teach some classes at CMU. So I guess maybe talk to us a little bit about some of your other things. So obviously, you're a professor. You have students that you're advising. What are some of these other initiatives that you've been working on in the past few decades?
Yeah, so you brought up JMLRs. I'm the
Yep.
co-editor in chief of
Mm-hmm.
JMLR. I
Mm-hmm.
think JMLR is a jewel in the sciences as a whole, in the sense
Mm-hmm.
that it's an open access journal
Mm-hmm.
where there are no publication fees.
Yeah.
Uh, it- it's a premier journal in the area of machine learning.
Mm-hmm.
And this, I think, is something that was, again, started by visionary researchers in AI,
Yeah.
where they said, why do we have these closed access journals where the editors, the editor in chiefs, the
Mm-hmm.
reviewers, all of
Mm-hmm.
them are researchers,
Mm-hmm.
and yet it's access, or for open access, you need to pay thousands of dollars, which, at big universities, it's not a big deal, but at small universities, it's a very big deal.
Mm-hmm.
And so we basically have set up all of the infrastructure and we are actually, as we speak, revamping our backend processes to make it even more efficient. But the
Mm-hmm.
key underlying principle
Mm-hmm.
is to have open access with no publication fees.
Mm-hmm.
And yeah, it's been very fruitful, um, getting a sense of the where the field of machine learning as a whole
Mm-hmm.
is looking at a few years down the line, right?
Mm-hmm.
Because you see these papers being published, and we have really grand
Mm-hmm.
ambitions of transitioning a lot of what these days are just incremental papers submitted to conferences,
Mm-hmm.
uh, because people just want to get what they are doing out there.
Mm-hmm.
And I think we need to revamp the entire publication culture. Again, that's a
Mm-hmm.
topic for an entire podcast.
Yeah.
JMLR has to play a very leading role, and we will come out with some of our plans for it very soon, but we are building towards that. We
Mm-hmm.
are modernizing the back-end processes
Mm-hmm.
with modern infrastructure,
Mm-hmm.
including AI infrastructure in mind.
Mm-hmm.
And once we have that ready, we will be ready for, I think, the next phase of um, I think, publication culture.
Mm-hmm.
Because JMLR 20 years ago, I think it provided a new path for journals
Mm-hmm.
as a whole. And I think what we are going to do in
Mm-hmm.
the next year or so is like showcase a new path for publication culture as a whole. So
Mm-hmm.
more
Yeah.
news on that very soon. But
Yeah.
yeah, it's so that's
Okay. Yeah, I think
um,
in our next time here, we'll just start getting into maybe a little bit more about some of your research. So I guess like we can maybe split into two parts. One
mhm,
about some of your like foundational contributions before 2023. And I think within that we can get into like I think you had
mhm,
some work on high dimensional statistics and graphical models, like your sparse additive models and high dimensional Ising model selection. And then you had some work in optimization theory and convex analysis, like dirty models for multitask regression. You also had some work in like sparse and inverse covariance and algorithmic tools. So okay, so I'm assuming the audience might not be intimately familiar with all of this work. So maybe give us like a spark notes on some of this research, maybe some highlights of some of your foundational contributions, and then afterwards we can get into some of the exciting stuff with neurosymbolic learning.
mhm. Yeah, absolutely. Um, One of the questions that was always animating me was uh, in machine learning, we have data, right?
Mm-hmm.
And these days, people just talk about images and text, which is a very, very specific form of specific data modality. But
Mm-hmm.
if we just think about data very broadly,
Mm-hmm.
how do we learn a model
Mm-hmm.
over such data? And if this data is noisy, you
Mm-hmm.
need a statistical model
Mm-hmm.
which can model the uncertainty over what you're seeing. And for one of the things that was always animating me was coming up with as general purpose statistical models as possible. And that's what the field of graphical models was all about,
Mm-hmm.
which is that if you have data that is very, very high dimensional,
Mm-hmm.
that there are a lot of variables
Mm-hmm.
that specify a particular system.
Mm-hmm.
And so think of a self-driving car,
Mm-hmm.
right? Most of its modalities are, well, if you're Tesla, it's just cameras, but if you're Waymo, you have a whole bunch of other sensors, right?
Mm-hmm.
And you can think of this really multimodal inputs,
Mm-hmm.
how to get a joint statistical model over all of these. That's what high dimensional statistical models, that's what graphical models are all about. And um, this was actually even before this whole deep learning boom took off, where you couldn't really fit these large deep neural models, but you still needed to model these large systems, right?
Mm-hmm.
So how can you do that? How can you decompose the system into smaller pieces and but at the same time, they are not all independent. How do they all come together? These are all of the questions that
Mm-hmm.
graphical models and high dimensional statistical models come into play. And
Mm-hmm.
what some of my foundational research did was think about provide very, very general frameworks for thinking about these questions.
Mm-hmm.
Uh, so one of my highest cited works probably is actually called a unified framework
Mm-hmm.
for high-dimensional statistical models.
Mm-hmm.
By the way, I have some issues with the way people um, talk about the bitter lesson. I don't know if
Mm-hmm.
you wanted to spend a couple of minutes on that, but
Mm-hmm.
you know, so I'm sure your audience is aware of the bitter lesson, right?
Mm-hmm.
Which basically says you shouldn't, as far as possible, not try to inject structure. So a lot of it made sense in the context of natural language processing.
Mm-hmm.
If you, let's just say, I want um, to named entity recognition, figure out, given a word, what is it a person, is it a place, and so on.
Mm-hmm.
And I can think of a lot of linguistic structure I can impose, a lot of domain knowledge I can impose,
Mm-hmm.
linguistic domain knowledge. But what people found is that if you had larger models and more data,
Mm-hmm.
that it always performed better, right? And so
Mm-hmm.
the better lesson is you are better off
Mm-hmm.
focusing your attention on gathering more data, gathering more compute, and being able to train bigger models
Mm-hmm.
rather than imposing structure. But the bittersweet lesson, if I were
Mm-hmm.
to coin a new phrase, is that you cannot violate the laws of math, right?
Mm-hmm.
And one of the key theorems in the field of machine learning is that if you do not provide any information about the target,
Mm-hmm.
providing data is not enough.
Mm-hmm.
Where I can come up with interpolations of the data
Mm-hmm.
that are going to be perfect on your training data, but that are horribly bad on
Yeah.
test data.
Mm-hmm.
And you can provide more and more data, and it doesn't really matter,
Mm-hmm.
right? So clearly, we need something more. And somehow we are able to regularize our learning,
Mm-hmm.
so that we are able to learn models that are simpler than just a horribly complex
Mm-hmm.
interpolated model.
Mm-hmm.
And the whole field of machine learning is how do you provide that structural
Mm-hmm.
effective bias? How do you provide this information about what the target function is?
Mm-hmm.
And if you do not,
Mm-hmm.
again, there are mathematical no free lunch theorems to say that you cannot learn, right?
Mm-hmm.
And so I think people are drawing the wrong lesson from the bitter lesson, which is that you don't need to impose structure. Like
Yeah.
so this violates the no free lunch theorem. So anyway, so that's my point. And a lot of my research these days is really focused on, okay, let's formalize the
Mm-hmm.
way in which we provide this information.
Yeah. Gotcha. Okay, great. So I guess like getting into like some of the more recent research, I think there's sort of three main areas that we might want to hit, but I guess we can just do it one by one. Let's start with neurosymbolic and causal representation learning. So I think this is obviously like a really exciting field. I also think it's one that you've invested a decent amount into. For people in the audience who maybe didn't go to CMU or don't know about this, Pradeep actually taught a class in representation learning back in the fall. So he's been pretty invested in this. He also has several different papers on this. One of his papers, like From Causal to Concept-Based Representation Learning, which was in NeurIPS 2024, had another paper on like identifying general mechanism shifts in linear causal representations, another paper on likelihood-based differentiable structure learning. So I guess like some of your papers sort of explore frameworks that integrate causal insights into symbolic representation learning. Some of your papers talk about identifying and modeling structural shifts in causal systems using differentiable approaches. What do you think are some highlights of some of your work in this field?
Right. So a lot of this work you can put under the umbrella of neurosymbolic learning. So
Yeah.
what is symbolic learning? Um, a lot of the work that the field of AI and ML is focused on
Mm-hmm.
is uh, broadly deep neural statistical models,
Mm-hmm.
right? You have your data, and then you have some deep compositional architecture
Mm-hmm.
that processes the data and gives you the outputs, right?
Mm-hmm.
But if you go back to the 60s, the field of AI was using a completely different class of models that we can call symbolic
Mm-hmm.
models, where the AI researcher would come up with symbols
Mm-hmm.
in terms of what the system comprises
Mm-hmm.
of. Like, for instance, let's say I have a robot that wants to fold laundry, right?
Mm-hmm.
Now, I can basically just give images as input and fit a deep neural model
Mm-hmm.
to predict actions.
Mm-hmm.
But in the 60s, the way they would process is first of all, they wouldn't have a fully deformable towel. They may have a simpler object,
Mm-hmm.
but they would actually have variables corresponding to what piece of the towel,
Mm-hmm.
what are particular actions
Mm-hmm.
that the robot can take, right? Grasp would be a symbol and so on.
Mm-hmm.
And even now in robotics, by the way, a lot of the work is actually, there is a lot of the symbolic scaffolding.
Yeah.
And there was very little learning that was happening in the 60s.
Mm-hmm.
And the advantage of that is that there is a lot of reliability
Mm-hmm.
to know exactly what are the variables, the high level variables that are going into the system.
Mm-hmm.
But the problem with all of that is that somebody needs to come and specify all of the relevant variables.
Mm-hmm.
It's very difficult to do
Mm-hmm.
when your data, the input data is extremely noisy.
Mm-hmm.
It's not fully controllable
Mm-hmm.
and cannot handle uncertainty.
Mm-hmm.
And so the question that in neurosymbolic learning that is kind of the crucial question is,
Mm-hmm.
can you automatically learn these symbolic variables
Mm-hmm.
so that you keep these deep neural compositional architectures. Okay,
Mm-hmm.
so they take the raw data and they're processing it. But then on top of it, you have symbolic variables.
Mm-hmm.
So right now, you still have people just having, again, pre-specified symbolic variables on top, right? So I'm going to use deep neural architecture to predict, is there a pedestrian? Is there a cyclist? Is there a blah? And then have some rules on top. And they call this a neurosymbolic model.
Mm-hmm.
This is still unsatisfactory. You need to automatically learn it,
Mm-hmm.
right? The analogy I would give is subconscious and our conscious,
Mm-hmm.
right? So our subconscious, you can think of as, again, this deep compositional architecture, but somehow there's this interface going from
Mm-hmm.
the subconscious to conscious, which we do not fully understand, by the
Mm-hmm.
way.
Mm-hmm.
And that is extremely crucial, right?
Mm-hmm.
Yeah, like you all know, Harari, he talks
Mm-hmm.
about the cognitive revolution, though
Yep.
there's a little controversy of that. Around 100,000 years ago,
Mm-hmm.
something changed, right? There
Mm-hmm.
were pieces of the prefrontal cortex in primates and so on
Mm-hmm.
that was different.
Mm-hmm.
And the neural architecture in rats and deer,
Yeah.
right? So it is not that rats and deer just didn't have enough neurons.
Mm-hmm.
It's that primates had a slightly more specialized architecture
Mm-hmm.
that was able to extract symbols.
Mm-hmm.
And the question really
Mm-hmm.
is, so nobody went to 100,000 year ago primates
Mm-hmm.
and said, okay, these are the symbols you need to learn, right? There wasn't a black monolith that conferred symbols upon them.
Mm-hmm.
They automatically learn them.
Mm-hmm.
So the question is, can we do the same thing? And that's
Yep.
what the field of symbolic learning is about.
Mm-hmm.
And what a lot of these papers that you mentioned, they use causality as a way to automatically extract symbols. So, so that's might seem strange,
Mm-hmm.
but to describe that in one sentence, in causality, you can think of the entire field of causality
Mm-hmm.
as not just a single model, but multiple models.
Mm-hmm.
And so think of it as a family of models. And what are these family of models? They actually tell you what will happen if you intervene in the system.
Mm-hmm.
If you intervene in the system, you actually have a different model. And um, um, when I have a causal understanding of the world, I will automatically be able to infer this new model that I need to use.
Mm-hmm.
And what does this have to do with symbols? You can think of interventions as something that happens on symbolic factors.
Mm-hmm.
Or rather, humans, we only care about symbolic factors that can be intervened on by and large, or at least hypothetically intervened on. And it turns out that this particular insight is sufficient to automatically extract
Mm-hmm.
these hidden symbolic factors.
Mm-hmm.
And it's a very, very um, exciting era.
Mm-hmm.
Now, the thing that fascinates me is that even with humans, right, a lot of our mental machinery is so much more suited to causal learning than statistical learning.
Mm-hmm.
Right? You can, if you have nieces or nephews, right, you can ask a 3-year-old um, about cause and effect, right?
Mm-hmm.
You can push something off the table
Mm-hmm.
and they would be able to understand cause and effect. If you ask them to explain correlation,
Mm-hmm. Yeah.
right?
Yeah, gotcha. Okay, cool. So, in maybe like the next like 1 or 2 minutes, tops, let's hit LLMs and representation theory, and then foundational theory and SSL and kernels. So, I mean, you had a few papers on this on this. I guess we don't necessarily need to get into the titles, but one of them focused more on like the associative memory mechanisms and transformer models. Then you had another paper where looked at like LLMs for guiding feature selection tasks. So I guess maybe talk a little bit about some of your work on the LLM side for like maybe a minute or two, and then we can get into foundational theory and SSL and kernels, and then we can start to close out.
Yeah, I think one of the nobody can deny that the modern foundation models are just miraculous, right? We
Mm-hmm.
have solved the Turing test, which is, I think, an amazing advance over the last few
Mm-hmm.
years. So a big question is, what are the internals of these models? What are these
Mm-hmm.
models actually learning? That's the
Mm-hmm.
question of representation learning.
Mm-hmm.
And we currently do not have a good understanding of this very, very key, simply stated question. And
Yeah.
a lot of my research is targeted towards that.
Yeah.
And we are making more and more progress towards
Mm-hmm.
this. And a lot of my research on neurosymbolic AI is
Mm-hmm.
also leveraging these modern foundation models and our understanding of their representations.
Mm-hmm. Awesome. And then you also had sort of category on foundational theory and SSL and kernels. So I think you had a few different papers here. You want to talk a little bit about some of your work where you're providing some insight and self supervision and kernel methods.
So one of the fascinating things we found is that um, the internals of deep neural models,
Mm-hmm.
there is this technical notion of identifiability, meaning that
Mm-hmm.
just me providing the data, there is a
Mm-hmm.
question of, does it pin down what are the internal functions the deep
Mm-hmm.
neural model is training?
Mm-hmm.
And what these papers are actually showing is that the internal functions
Mm-hmm.
of the model are exactly specified by certain function space operators.
Mm-hmm.
And a lot of the stuff like masking, and these causal autoregressive masks and transformers,
Mm-hmm.
all of them, they actually specify certain operators, certain contextual operators,
Mm-hmm.
and the internal functions are precisely factorizations of these operators. So that's what those papers are
Mm-hmm.
uh, showing, actually.
Gotcha. Okay, totally makes sense. All right. So getting into some of our very last questions here. So I think we've done a pretty maybe relatively comprehensive outlook on some of your research, but I think maybe the audience is a little bit curious about sort of what you're up to now, what you're interested in the future. So very exciting. You're going to be working on a startup. Maybe you want to like briefly talk a little bit about maybe at a high level what problems you want to solve or maybe what area it's in. And then also just like going into the future, right? This is a very, very, very fast field. It's growing incredibly fast, as I'm sure we both know very well. Maybe talk a little bit about some of the fields that you have more conviction in now. So I mean, we already talked about neurosymbolic, representation learning, some other stuff. Any like new, maybe emerging fields that you feel like you're really excited to work on?
Yeah, the so I'm working on a startup. It's called Woodwide AI,
Mm-hmm.
and actually, there's a little bit of a story as to why we called it that. It's based
Mm-hmm.
on the Wood Wide Web, so I'll just leave it
Okay.
at that.
Sure.
So our main goal is to bring to bear all the amazing advances that people have for images and text, but
Mm-hmm.
bring it to bear on numeric and tabular data.
Mm-hmm.
Like for students, we see that
Yeah.
language intelligence is different from numeric and quantitative
Yeah.
reasoning intelligence, right?
Yeah.
And what my work in neurosymbolic AI is making me realize is that we actually need new developments
Mm-hmm.
to actually make that possible.
Mm-hmm.
And, that's basically what we are
Cool.
building.
Mm-hmm.
Um,
It's awesome. Any sort of areas, maybe research areas that you're very bullish on right now? I think AI for science is definitely an aspect that you've had some work in, as well as like a lot of other professors at CMU. When Zico was on the podcast, we also talked about AI for science. I assume you're probably relatively bullish on it, but maybe in like the next 30 seconds, any other speed run, any other topics that you might be excited about?
I suspect that even more than AI for science,
Yeah.
it's good AI for the common man. is, I
Okay.
think,
Yeah, yeah, yeah.
I'm extremely bullish on.
Mm-hmm.
It's really going to improve our quality of life in so many ways.
Mm-hmm.
That is actually a big reason why I'm building this startup, because
Mm-hmm.
that cannot happen unless we also make numeric intelligence possible.
Okay.
But assuming given all of the advances,
Yeah.
I'm certain that we will succeed in this. I think, yeah, AI for the common man. That's what I'm bullish on.
Okay. Awesome. Any research areas that you're excited about? that you think are you're more bullish on, or mostly just some of the things that you've worked on in the past?
I think more on, again, it kind of jumps off of this, um, being able to understand context,
Mm-hmm.
being able to ingest context, right?
Mm-hmm. Yeah.
For instance, have so much context in your head.
Mm-hmm.
How do you communicate that to an AI model?
Mm-hmm.
Earlier, you had a label. Right
Mm-hmm.
now, people say, "Oh, you will just talk to the AI model, or it'll have access to your journals." But
Mm-hmm.
what if you don't have journals, right?
Yeah.
And how much are you going to put an AI model? How do
Yeah.
you try? I
Yeah.
think that's what I'm extremely bullish on. More needs to be done, but
Yeah.
people are still about that.
Awesome. Well, thank you so much for coming on the podcast. Really appreciate it.